Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives. In this episode, we'll be talking to Bill Coulbourne, PE, a structural engineering consultant and owner of Coulbourne Consulting, about the key changes in ASCE 722 wind design procedures that will impact the design of buildings for wind. I'm your co-host, Matt Cardle.
And I'm your co-host, Rachel Holland. Now let's jump into our conversation of the week with Bill.
This episode of the Structural Engineering Channel is brought to you by PPI, a leader in engineering exam prep for the PE structural exam. PPI provides expert prep courses and study resources designed to help you pass the PE structural exam the first time. PPI's PE structural course is fully updated and taught with October 2021 code references and includes new editions of their PE structural books. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. When you take a live online course, PPI guarantees you will pass, or you can take the on-demand course for free. PPI has helped engineers achieve their licensing goals since 1975. Check out PPI today at PPI2pass.com to see all of the resources available for PE structural exam prep. Again, that's PPI2pass.com.
Bill, welcome to the show. We are delighted to have you here with us today. Can you briefly introduce yourself and let the listeners know what you do on a daily basis?
Sure. So my name is Bill Coulbourne. I'm a practicing structural engineer and was educated in college as a structural engineer. I have been involved in the design of facilities and the mitigation of damages done by natural hazards for about the last almost 30 years. So I have focused a huge part of my career on winds and flooding and tornadoes. For those that are on the West Coast, there were already tons of practitioners in the seismic business. I didn't think I could add much to that practice. But there are a lot of people, certainly in the 1990s and 2000s, that did not know a lot about how to do wind design and definitely didn't know a lot about flooding. So I've had the good fortune of focusing on both flooding and high winds. And there's been a lot of work to do in that area. What I do on a daily basis is I used to work for large engineering firms, and those firms had contracts with FEMA. So I mostly for the first 15 years or so, did work that related to what FEMA wanted engineering consultants to do for them. Some of that was damage investigations after major events, mostly hurricanes and tornadoes. Some of it was the development of new guidance on how to design for tornadoes and high winds and flooding. And some of it was education. So, I mean, I've delivered a ton of webinars and seminars, both for ASCE and for FEMA and for other continuing education developers on those topics. Now I'm not working quite so much, and I'm working only for myself and have for the last 15 years or so. So I mostly pick and choose what I want to do depending on what kind of problems somebody presents to me. And so that's what I've been doing and what I have done on a daily basis.
Cool. Thanks so much for that, Bill. Very impressive profile. Besides doing all that, you also co-authored an article in the October 2022 Structure magazine. It was called the ASCE 722 Changes to Component and Cladding Wind Provisions. That lists, the key changes. Can you explain a little bit about that and in your own words, what the big impacts are in terms of wind design for buildings?
Oh, sure. Absolutely. So as part of my, work over the last 30 years, I've participated in both the wind load subcommittee and the flood load subcommittee of ASCE 7. So I've had a chance to participate in the development of on new and ongoing engineering standards for those topics. And so every 6 years now, ASCE publishes changes to their provisions for natural hazard loads. And the document that you referenced, the article that you referenced, was written as part of the work that we did for ASCE 722. And so the provisions that were written about only focused on component and cladding loads. So those are the loads that are developed on what I'll call the skin of the building. So the siding, the doors, the windows, the roof, the attachments to the building. All of those elements usually see higher wind pressures than the structure does, than the frame does. And so there were a number of significant changes made to those component and cladding provisions in 722. And someone on the Structural Engineering Institute editorial board, the Structure Magazine editorial board, asked me if I would write about those changes. And so that's what prompted the article. I think what practicing structural engineers should see and how it'll affect building design is that hopefully our intent was to make the provisions in 722 simpler than they were in 716. We reduced some what turned out to be not all that needed steps in some of the processes to get loads on component and cladding. And so hopefully practicing engineers will see that it's hopefully a little easier. And there are a number of cases where, in fact, they'll see the loads go down for components and cladding, which, of course, is a benefit to the structure cost.
Yeah,
Interesting.
Smaller loads and making it easier. I was just going to comment. Yeah, thank you. For the engineers, go ahead, Rachel.
So I know there were like a few changes about this, but one of the first changes was the added provisions for the tornado wind loads. You want to go ahead and talk about those a little bit more?
Yeah, sure. So I would say over the last 10 years or so, we've seen a lot of tornadoes hit various parts of the U.S. with significant damages, and in many cases, unfortunately, a number of people killed by those tornadoes. And so I would say it's been the last 10 years or so where there's been a huge amount of interest by practicing structural engineers and by clients or by building owners. How in the world do I help design my building so that I either don't lose people, people don't die in it, or that it's easier to recover? And so in the 716 version, we wrote a pretty large segment in the commentary about how to do it. And what the elements of tornado design were and which ones were the most important. But we still didn't know a lot in 716 about some really important elements of tornado design. So I didn't, and other members of the wind committee didn't feel like we were ready to take all that to the practice and put it in the body of the standard where it has the teeth of law, where it can be adopted by the building codes, et cetera. So we chose to wait in 716 until we thought we had more data. And I got to tell you, the research community, particularly, really took a huge interest in this. The NSF provided some funding for some research in the area. A couple of firms donated an extremely large amounts of time and effort to help put the tornado loads together. And so the developer, the leader of that tornado load group, put everything on tornado loads now in one chapter 32 in ASCE 722. And so now all the information is in a chapter where practitioners can easily find it. The most important things about it, I think, there's a lot, and it's probably more than I can do here, but there are a couple of really important things. One is there have been tornado hazard maps developed. So now we finally have a way to define the hazard for a tornado in any part of the country, and it's maps. And so that's a really important inclusion in this chapter. The second is that the committee felt like we should mostly focus on risk category 3 and 4 buildings for tornado loads. Let's not try to design every house for tornado loads. Let's not try to design every storage structure for it, but let's focus on risk category 3 and 4 buildings. And so I think those are the two primary drivers. There's a lot of small technical details that are important to the loading. But I think what practitioners can look for is, in one chapter now, a place to help them with how do I design for tornado loads anywhere in the country.
I had a follow-up for that one. For those of us in the West Coast that deal mostly with seismic and not with tornadoes and wind,
Right.
I guess how much load are those in the tornado tables? Is it, yeah, I guess what does that look like compared to typical wind loads?
Well, so I'm going to do this off the top of my head, which is extremely dangerous.
Okay, disclaimer.
Yeah, I needed that disclaimer. So if you're let's say you're in the middle of the country in or near Tornado Alley. So you're in Iowa or Kansas or someplace in Texas or Oklahoma where, tornadoes are a frequent occurrence. And if you were to design a normal building for a risk category 3 or 4 building, normal building for wind loads for those two risk categories, you would be looking at wind speeds, I think, in the range of 120, maybe 125 miles an hour. Tornado loads are developed in those parts of the country for 250 miles an hour. And wind pressures are a square of the velocity. So the pressures go up extremely,
that's significant.
That's a significant difference. If you're looking at the extremes of what would you normally design those buildings for in the center of the country versus what would you design the building for the worst tornado. So 250 miles an hour is an EF5, Fujita scale 5 level tornado. So I'm looking at extreme. I'm trying to remember what the extremes are, but it's pretty significant.
Yeah, I think just the 200 plus miles per hour gives you an idea for the ones we typically do.
Let me add one other point to this, that just so that practitioners can get a sense of this. But that doesn't mean the standard wasn't written so that every risk category 3 and 4 building had to be designed to a tornado. It does give you wind speeds for various parts of the country, for various risk categories, and for various return periods. But what you're supposed to do is compare the tornado speed with what the normal wind design speed would be, and then pick the most restrictive. And what we've learned in tornado design is the bigger the target you have, meaning the bigger the building, the more likely you are to get hit. So the wind maps also have a level of specificity with them about the plan area of the building. So if you have a 2,000 square foot building like a house compared to a 300,000 square foot building like a warehouse, you're much more likely to see a tornado hit the warehouse than you are the 2,000 square foot house. And so that's part of the hazard development that went into the tornado loads.
Yeah, interesting. And another provision that I think that was one of the changes was to remove tabular methods of wind pressures from chapters 27, 28, 28 and 30. Could you tell us more about that? I know for us in the structural engineering community, we're used to going to those tables in the ASCE 716. So what does that mean? Or what does that look like?
I know you are. Well, so here's what drove that decision. Two primary things. One is, as time has gone on, from the very first time tabular methods were put into the standard, and then were subsequently, captured and put into some portions of certainly the residential building code, the IRC. What's happened is, more and more engineers are using some sort of computer program to find wind loads, along with all the other loading that they do for their design. And everybody has a computer, and everybody has Excel, and everybody can use a formula, and everybody can input it into formulas into Excel spreadsheets. And there just didn't seem a need to keep publishing tables that had to continuously be updated if you made a small change in the provisions. And I don't remember whether you remember, Matt, or not, but there's pages and pages and pages and pages of tables.
Oh
So
yeah, I
it's
recently
a
took the essay.
it's a lot of updating to do if you even make one small change, and it's prone to error. And so the committee felt like everybody can do this on their own. They don't need a table to figure out what the wind loads are. Now, we got a fair amount of pushback about that from some practitioners, some parts of the industry, but we still felt like we can figure out how to deal with this. Every engineer can figure out how to do this. Engineering firms that do lots of work in wind design can make up their own tables. Every engineer doesn't have to do it. You can, do it as a standalone for Simpson Strong Tie or for any other engineering firm in the country. So that was what was behind it. Plus, we also save a lot of pages.
Oh yeah. So is that essentially you're just giving the engineers the formula and then they can do their own spreadsheet instead of giving them the whole tables?
Exactly. And the formulas have all been in the standard all along. It's not like they're new to this version. The formulas have been there all along. So people could have, and a lot of practitioners that I've talked to over the years had been doing it that way anyway. They've been doing it themselves, by just using an Excel spreadsheet or something similar. So
I think the biggest thing with that, it just sort of eliminates errors, which are sometimes just they happen, easy.
They do. They do happen. But I got to tell you, after trying to revise some of the tables as a member of the committee, they happen on the committee's end too. So there's sometimes no guarantee that what's published is 100% accurate, because all the effort in the committees is primarily volunteer effort. So everybody's doing it, on their own nickel, so to speak. And so I think this is the right move. I hope it turns out to be the right move, but that's what the committee felt like. This is how we should move forward. So,
yeah. One other thing, you touched on it a little bit at the beginning, but revising the component and cladding charts for the pressure coefficients,
right?
And you sort of simplified that process. So, can you share with us a little bit more about that?
Sure. So, I have to do a little history here. So, in the 716 standard, there was a lot of research done by several wind tunnel organizations. One of them primarily was the University of Western Ontario. There's a couple of people that sit on the wind committee from that university. They have a wind tunnel that's worked on low-rise buildings, particularly quite a bit. And they and a couple of other folks had done a lot of work on the external pressure coefficients that we use to define the pressures for components and cladding. And so from 710 to 716, all that research work had been done. And then in 716, they came forward with proposals to revise those coefficients. And in most cases, those revisions drove up the pressures on components and cladding. The primary reason that they drove them up was that if you've done wind design on components and cladding, you know that our primary driver for the pressures is what we call an effective wind area. So the area that is affected, that the wind affects on the siding. So it could be a piece of siding, or it could be a screw that's a fastener, or it could be a nail that fastens part of the roof. Well, the smaller that area is on our wind charts, the higher the pressures. So we lose the distribution, if you will, of wind pressures across larger areas. So all of those smaller wind areas drove up the wind coefficients that were used in the charts, which of course then in turn drive up the pressures. So what we found in looking at this again for this 722 cycle was we know a lot less about what those size of those effective wind areas really ought to be. And we thought and had lots of conversations about how the effective area is actually really larger than what we've said it was in 716. There's a lot more load sharing going on between fasteners and between pieces of siding. So we capped all of the very small effective wind areas at 10 square feet. There used to be a few that were like 6 square feet, 2 square feet, 1 square foot. Oh my God, well, the wind pressures for those areas are just huge. So we capped everything at 10 square feet. There's nothing smaller than 10 square feet. And on the higher end, we tried to cap everything on the high end at 100 square feet, but we weren't being true to the value of the coefficients really. So, but we did simplify it by making it either 100, 200, or 300 square feet, nothing larger, and no 250 square feet, no 325 square feet. It's square feet. Listen to me. So it's either 100, 200, or 300 square feet. And then there were some complications for 45-degree roofs and whatnot. We simplified those, and we simplified the way you find pressures on overhangs. So I hope, and the article addressed, those primary changes, and then offered a very small snippet of an example so the practitioner could see what the differences in pressures were before and after the change for a couple of locations in the country. So
I think that's great. Yeah, I think that the engineering community always appreciates when things are simplified when they can be. So
right.
Hopefully that'll go over well.
I hope so.
Yeah, very true. Definitely appreciate that. There was another thing that was added was the provisions for ground-mounted solar arrays. How did that come about? Was there a big demand, and what does that look like?
So this was driven also by a little bit of history. So in 716, we added roof-mounted solar collectors to the standard. And that was primarily driven by you folks on the West Coast.
Yep.
There was a lot.
We have a lot of those.
Well, yeah, there was a lot of demand for roof-mounted solar arrays. There was nothing in the standard about how you handle the wind loading on those things. The Structural Engineers Association of California wrote a standard that was being followed. At least at the time, at least between 710 and 716, a lot of people who were interested in the issue were manufacturers, but they wouldn't publish the data because it was proprietary. So if you did a wind tunnel study, I don't even know the names of most of the solar companies, but if you did a wind tunnel study for one of the solar companies, all that data ended up being held close to the vest because it was proprietary. So we made a change in 716 to publish information on roof-mounted solar collectors. And then between 716 and 722, and not only on the West Coast, but many places here on the East Coast, you start seeing solar farms popping up all over the landscape. But there was no guidance on how to handle wind loads on solar arrays mounted on the ground either. And the ground can be at airports and roofs of parking garages or parking canopies or whatever. There wasn't any real guidance from the profession about how to handle wind loads on those features. So we took we followed the logic sort of. We'd done something for roof-mounted solar arrays. We probably ought to do something for ground-mounted solar collectors because they're becoming a lot more popular. And so that's what we did. And there are a fair number of manufacturers on the ASCE 7 wind load committee. So, we had a lot of help to come up with what were the arrays to look at and what were the provisions, what should the provisions cover.
So another one of the provisions that discusses elevated buildings, there was a change made for that as well. How will that impact the design process for structural engineers?
So, and this has a tiny little bit of history too. When we started looking at ideas for things that we ought to talk about, or cover in 722, one of the committee members made the astute observation that, we're designing a ton of buildings on the coast to handle hurricane and loads from nor'easters. And most of those buildings, certainly near the coast, are elevated. And we have no guidance on what to do with the wind provision, what the wind loading is for the underside of elevated buildings. And yet we've got thousands of them all along the Atlantic and Gulf Coast. So the question was, well, why can't we, let's see if we can't come up with something. And prior to having these provisions, I think most practitioners would say, well, the underside of a building is the opposite of a roof. So let's take the roof provisions and just flip them over and use the provisions for roofs on the underside of a building. But there's a lot of differences to that. I mean, you're not that far off the ground usually. Many elevated buildings have access places, on the ground, so they have entrances and stuff that block the wind flow. And so a subset of the wind committee, who had done a lot of wind tunnel work and who were very familiar with engineering along the coastlines, came up with these provisions, and that's how it came about. Hopefully it will. I don't know that it's going to change the loading that people have been using, but at the very least, it'll give them something based in science, or based on science, based on the best thoughts that members of the wind engineering community have about how to handle this particular element of the building. And so hopefully, at least the responses, the answers you get for wind pressures on the underside of these elevated buildings will be more accurate. So that's how it came about.
Yeah, that's interesting. Yeah, like you said, a lot of them are elevated, and yeah, I guess you could flip it upside down, engineering judgment, but then now it's based more on, okay, here's what the actual science is. There's some science behind this now.
Exactly. And it's a consistent way to do it for everybody. It's not before you'd have, you could use your engineering judgment, but you put 1,000 engineers together and you get 1,000 different answers. So that's not good for the practice either. So
yeah. And the last change in the provision was that there was an added section for rooftop pavers. And to clarify, rooftop pavers, those are the ones where, I don't know, let's just say you have a concrete roof and then you put some fancy tiles that are elevated on top of that deck. Is that what the rooftop pavers are, or how does that affect it? Or can you go more into that?
Yeah, exactly. So, usually the rooftop pavers sit in a frame. So I would liken it to a frame that's got a whole bunch of squares or rectangulars molded into it. So for the sake of argument, let's call it a plastic frame. And those elements that are molded into it are exactly the size of the pavers. And you put a paver in each of the slots. And what that does is help add weight to the roof. So in most cases, it's put on a flat roof, and it's put on a roof that is like a single ply membrane, or maybe a ballasted, well, not usually a ballasted roof, but a roof that is tarred down. So it's a single ply that's held, adhered with a mastic or a tar of some sort. And then the paver acts as ballast for it. So it's weight. And the paver sits above the roof a little bit so that there's wind pressure equalization between the top and the bottom of the paver, so that then the pavers don't lift off. You haven't helped yourself much if you lose the pavers in a high windstorm. So that was added because there was a significant increase, or so it appeared to the committee, in the use of those kinds of pavers and roofing systems across the country. So, and that's how most of the changes are developed. Developed from one cycle to the next is, what does the committee and the members of the committee see in real life, in real practice, that needs to be addressed that currently is not addressed as it relates to wind. So,
yeah, I've had a few rooftop pavers on some of the projects that I've been working on, and yeah, a question comes up with, yeah, I guess those are technically components in cladding, but not really. So there isn't really a wind provision, but now there's going to be a wind provision for that. So
right.
Yeah, it's interesting.
And it is in the components and cladding section. So that's where it is.
Oh, great. Yeah. Because of all these things, it's, oh yeah, I've seen some of these and, in the industry, and it's great to see that the committees are keeping up to date with everything. So appreciate that.
Sure.
Thanks so much for sharing, Bill, about just how the changes come about, and also obviously for providing insight on the changes that are here. So One thing that Matt and I always like to ask, just to sort of wrap this up, is if you have any, like a final piece of career advice for structural engineers on just, their career and how, maybe to avoid making costly errors and just to, be the best engineer that they can be. What would be your final piece of advice?
Well, mine would be, and maybe you all have had this somewhat the same experience. I was in the industry for a while before I actually found this work in natural hazards to really connect with me. And it was something I got passionate about. And it was easy to kind of get passionate, I think, because I got a chance to go to disaster sites and see all of the devastation that happens from tornadoes and flooding and hurricanes, and feel like as an engineer, I needed to do something about it. And as a practice, we needed to work on this problem because it's large. And so it was easy for me to get passionate about it. So I would encourage every practicing structural engineer to find something you love, find something you'd like to be engaged in, and not just have a job, but find something that really, seems to matter to you. And it doesn't have to be buildings, and it doesn't have to be hazards. It could be bridges. It could be large pieces of infrastructure. It could be climate change. I mean, there's so many things that are in our collective wheelhouse that I think is just an almost endless opportunities for people to, find something that really they enjoy and that matters to them. And then I would just, I'll call it, I'd work it. I mean, and by working it, I mean, find people that you appreciate and that can mentor you, that can offer new ideas about how to do stuff, that can guide you about, where are the best conferences to go to, how should you write a paper to present it to, either clients or other engineers to engage and judge what they think about your ideas. I would get on some sort of, I'd belong to some organization that helps you advance, ASCE or one of the institutes or the American Concrete Institute, whatever organization you think matters the most to what you do, and get engaged and be part of the solutions and not part of a problem. So that's what I would suggest people do, and that's what I see young people doing. I see ASCE introducing all kinds of new engineers to the ASCE process, and I love it. I'm so happy that people as old as me don't have to keep doing this. And that there's a huge amount of interest on the part of young people to participate. And the same goes with you two. I mean, doing podcasts and stuff. This is a great way to offer information out to the practice. So I applaud what you're doing.
Thank you. That's excellent advice as well. Thanks.
Sure, absolutely.
Yeah, thanks, Bill. Really appreciate the time you've given us and for summarizing and giving us some of the, I guess, the backgrounds and some of the history that goes into these provisions. That was really insightful, and I didn't really know about some of the history that goes into these things. So really appreciate it and appreciate the summary.
Absolutely. Thank you both. I appreciate it.
I hope you enjoyed the episode today. We'd love to hear your feedback, comments, and or questions. To leave them, please visit structuralengineeringchannel.com. You will find a summary there of the key points discussed in today's episodes, which is episode number 92, as well as the links to any of the resources, websites, or books mentioned during the episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you the best in all of your structural engineering endeavors.